Welcome to going over the General Physics Unit 1 end of topic test that should have taken no more than 1 hour and 15 minutes, as it was an 80-mark exam, just like it would be in the actual final exam. So let us go over this one question at a time. Question number 1. A driving instructor gives a student a sudden order to stop the car in the shortest possible time. Figure 1.1 shows the speed time graph of the motion of the car from the moment that the order is given. The order to stop is given at time t equals 0. Now here the examiner's making it quite clear that the order to stop the car was given at the very beginning of this graph. State the speed of the car at time t equals 0. Well, I hope after reading you can get quite easily that the answer is going to be 18 meters per second. Suggest why the car continues to travel at this speed for 0.9 seconds. Now this is the first part where we might argue that it's got a little bit more challenging and you really need to think about the answer. So the order was given at 0 seconds, but the student doesn't start hitting the brakes until 0.9 seconds. Why is that? The reason, because that's how long it had taken the student to react. It's the driver's reaction time that stopped the student from braking immediately. Calculate the deceleration of the car between 0.9 and 4 seconds. Well, deceleration is negative acceleration. A equals v minus u over t. And quite clearly here the final speed is 0. The initial speed is 18. And the time taken is 3.1 seconds. So if you rearrange all of this, the deceleration is 5.8 meters per second squared. Look, if it's rounded, don't worry about it. Okay. The total distance travelled by the car from t equals 0, well, this is area under the graph. Remember, the gradient of a speed time graph or velocity time graph gives us acceleration. Why? Remember, gradient is change in y over change in x. The change in y here is speed. The change in x here is time. Rise over run gives us the acceleration. In other words, the steepness of the line gives us the acceleration. The area under the graph gives us distance. So distance equals speed times time. We've got two shapes here, a rectangle and a triangle. The rectangle is 0.9 times 18 and the triangle is 3.1 times 18 divided by 2. And if you add all of this together, you should get 44 meters. Okay, now remember, distance is meters and speed is meters per second and acceleration is meters per second squared. Guys, units is really important. It's very important that you get them right, and it's important that you state them properly. Describe and explain a danger to a driver of not wearing a safety belt during a sudden stop. Now, there's numerous ways to express this answer, but basically, if the driver doesn't have a seat belt and he hits the brakes, well, his body or her body is going to continue to move at the same speed it was moving at before he hit the brakes. So the body's going to keep going forward because the body has inertia, the body has momentum, however you want to describe it. The body's not really going to stop. What's the danger? Well, the driver could hit their head off the steering wheel. It could go through the windscreen. They're not very nice things to think about. So the seat belt prevents that from happening. I hope that makes sense. Question number 2. Figure 3.1 shows an oil tank that has a rectangular base of dimensions 2.4 meters by 1.5 meters. The tank is filled with oil of density 850 kilogram per meter cubed to a depth of 1.5 meters. Calculate the pressure exerted by the oil on the base of the tank. Well, with regards to fluids or liquids in this case, pressure is density times gravity times height. Pressure in solids is force divided by area. It's the oil that's causing pressure on the solid base. So the formula that we should use here is pressure equals density times gravity times height. And if you multiply these together, 850 times 1.5 times 10, it's been rounded here to 13,000 Pascal or newtons per meter squared, but the answer is actually 12,750. Don't worry about the rounding. A more complex way of doing this, but would still be right, would be to do pressure equals density times gravity times volume, but then dividing that by the area, which ultimately gives you pressure equals density times gravity times height in any case. And the answer would be exactly the same. What happened here a lot of the time was people either doing pressure equals density times gravity times the area or times the volume instead of really focusing on what was the most important part, the height. What's the force exerted by the oil on the base of the tank? Well, now we're looking at the solid aspect of the tank. And pressure equals force divided by area, or force equals pressure times area. The pressure of 12,750, but times area of 1.5, which is one side of the base, times 2.4, which would have given you, if rounded, 46,000 newtons. Now remember, you don't have to round, and there is more than one way of doing this, where you could basically focus on the weight of the oil rather than what I've done here, which to me is the most straightforward way of using pressure, force and area. Part B. The force calculated in A Part 2 is the weight of the oil. Calculate the mass of the oil in the tank. Well, if you know the weight of the oil, to find the mass, weight equals mass times gravity. So mass equals weight divided by gravity. Again, using the rounded answer here. If yours is not rounded, don't worry. It's 46,000 divided by 10, which gives you 4,600 kilograms. I think the actual answer was more like 4,590 kilograms. Part C. When he is checking the level of oil in the tank, a man drops a brass key into the oil and it sinks to the bottom of the oil. State what that shows about the density of brass. Well, brass is quite clearly more dense than the oil itself, therefore it sinks. It then says, explain how attaching the key to a piece of wood would prevent it from sinking. Well, the idea here is wood is less dense than oil, which is what a lot of you said. However, the key's attached to the wood. So what they were really looking for here is the fact that the overall density of the wood and the key is less dense than the oil. Therefore, it floats. The example I gave in class was, why is it an oil tanker floats in water even though it's made of metal? Well, the oil tanker has also got a lot of air inside it because of the compartments where people live and cook and etc. And it's also full of oil, which is less dense than water. So collectively, the overall density of the oil tanker is less dense than the water, so it floats. So here, what we're looking for was the overall density of the oil with the wood and the key attached being less dense than the oil. So the key attached to the wood is less dense than the oil. Question number 3, define density. Well, the formula for density is mass divided by volume, or more correctly, mass per unit volume. As I've explained, if you're going to write the formula, you must write it in words, okay, for definitions. The proper definition is saying the formula in words, which is mass per unit volume. The density of aluminium is 2.70 grams per centimeter cubed. The thickness of a rectangular sheet of aluminium of foil varies, but is much less than 1 millimeter. A student wishes to find the average thickness. She obtains the following measurements. Mass of steel, 60.7 grams. Length of sheet, 50.0 centimeters. Width of sheet, 30.0 centimeters. Calculate the student's values for the volume of the sheet. Well, volume is mass divided by density, or here it's 60.7 divided by 2.70, which gives 22.48 centimeters cubed. The average thickness of the sheet, well, volume equals area times average thickness. So we've just found the volume. We can find the area by doing length times width. And then to find the thickness, we just need to rearrange volume equals area times the thickness, which would give us roughly 0.01499 centimeters. And then underneath, another student provided with a means of cutting the sheet decides to find its average thickness using a single measuring instrument. Assume the surfaces of the sheet are perfectly smooth. Name the measuring instrument she could use. Micrometer, screw gauge, or vernier calipers. Okay, but micrometer is the one that you've been taught, so that is the one that I would stick to. Describe the procedure she should follow to obtain an accurate value for the average thickness of the sheet. Details of how to read the instrument are not required. Okay, just like I said in lessons, you don't really need to focus on the actual instrument itself. Now, there's many ways of answering this. First, major points, check for zero error. Cut the sheet into several pieces and measure the thickness of several pieces, in other words, several sheets. Measure the thickness of several sheets together and then divide by the number of sheets to obtain an average. Repeat the experiment and take an average. All of these will give you the marks. Now, really what they were looking for, check for zero error, repeat the experiment, take an average is 1 mark. Measure the thickness of several sheets would be a mark, and divide by that number would also be a mark. Now, some people said don't use several sheets. They said fold it. Others said cut it into several pieces. All of these are ways of saying measure multiple thicknesses. So that would have been perfectly fine. Question number 4. Figure 2.1 shows a uniform rectangular slab of concrete ABCD standing upright on the ground. The slab has a height of 0.60 meters with width of 0.30 meters and a mass of 18 kilograms. A force of 40 newtons acts horizontally to the left at B. Calculate the weight of the concrete slab. Well, weight equals mass times gravity, which is hopefully straightforward enough. They've told us that the mass is 18 kilograms, therefore 18 times 10 is 180 newtons. The thickness of the slab is 0.40 meters. Calculate the pressure exerted by the slab on the ground. Well, pressure is force divided by area. And what we've got is we've got a length of 0.30, and they've told us the thickness, which we can't see in the diagram because it's only two-dimensional here, is 0.040. So pressure is force divided by area. 180 divided by 0.3 times 0.04, and that gives us roughly 15,000 pascals. Remember, again, don't worry if it's been rounded. And this arrow that you see here is for a question on the next page, which asks about drawing an arrow from the center of mass. Well, quite clearly, the arrow for the center of mass has got to be in the center, and it's got to be going down the way to represent weight. So that arrow that you just saw there is for B part 1. On figure 2.1, draw and label an arrow to show the weight W of the slab acting on its center of mass. Now, the one thing that I did not do here is label it, which is something that I should have done. I should have labeled it weight, but the arrow is there, and this is what you would have had to have done in the exam. Incidentally, because I didn't label it weight, I would have lost the 1 mark that was on offer. Calculate the moment of the force of the 40 Newton force about the pivot D. So as you can see here, force times perpendicular distance from the pivot. And if I go back to the diagram, you'll see that it's 40 times 0.60. So they're saying the pivot is D. There's your perpendicular distance of 0.6. There's your force of 40. And that would have got you 24 Newton meters. The weight of W about the pivot D, or the point D. Again, moment equals force times perpendicular distance. This is where a lot of mistakes were made. Why is it 180 times 0.15? Well, if I go back to the diagram, this whole thing is 0.3. So half of it is 0.15. Your pivot is the point D. Here's your weight of 180. So it's 180 times 0.15, which would have given you 27 Newton meters. Part 3 asks, the ground is rough so that the slab does not slide. State and explain what happens to the slab as the horizontal force of B is gradually increased. A lot of people did this very well, actually. They realized that the anti-clockwise moment caused by force B was going to be bigger than the clockwise moment caused by the weight. Now, why? Remember, here is the pivot. This is where you're tipping it over. And this is going in the clockwise direction, and this force is going in the anti-clockwise direction. So if you make that bigger, and they've told you that it's not going to slide, then it's going to tip over towards this side here, the anti-clockwise side. So anti-clockwise moment was bigger than clockwise moment, so the block would have tipped over. So moment of force at B becomes bigger than the moment of the force at W. Again, as I've said, anti-clockwise is bigger than clockwise. Figure 3.1 shows an aeroplane of mass 3.4 times 10 to the 5 kilograms accelerating uniformly from rest along a runway. After 26 seconds, it reaches a speed of 65 meters per second. Calculate the acceleration of the aeroplane. Now, this question is certainly hinting towards Newton's second law, F equals ma. But for the first part, it's the other formula, which is A equals V minus U over T. Final velocity 65 minus the initial velocity 0, because it started from rest, divided by the 26 seconds, which gives 2.5 meters per second squared. Now, the big mistake here was a lot of people wrote 2.5 meters per second, but forgot the squared. Meters per second is for velocity or speed. Meters per second squared is for acceleration. Calculate the resultant force on the aeroplane. That's F equals ma, which is 3.4 times 10 to the 5, the mass that was given, times the 2.5 meters per second squared, which is the acceleration that was found, which gives 8.5 times 10 to the 5 newtons. Now again, don't worry about rounding, and don't worry if you didn't put your answer in standard form. But no unit, you would definitely drop a mark. Now, something that's typical of paper 4 In part B, just after taking off, the aeroplane continues to accelerate as it gains height. State two forms of energy that increase during this time. Now we're looking at forces mixed with energy in one question. If it's accelerating, kinetic energy will certainly increase, and since it's going higher, gravitational potential energy will also increase. We also accepted heat or thermal for this particular question. State one form of energy in part 2 which decreases during this time. Quite clearly chemical energy, because the fuel from the plane is being used up. Heat would not be accepted here. Part 2, state why the total energy of the aeroplane decreases during this time. Remember, energy cannot be created or destroyed. It changes from one form into another. And what they're asking here is, why is it not a perfect conversion here? Why is it not all going to GPE and kinetic? Why is the chemical energy not changing all to these two other forms? Well, basically, because the plane will be working against air resistance. Okay, so there's going to be energy transferred to the surroundings as thermal or heat or sound. Either of those would be acceptable. Kinetic energy of the air, in other words, the plane is causing the air to move. Part C, back to forces again. When the aeroplane reaches its maximum height, it starts to follow a curved path at a constant speed. State the direction of the resultant force on the aeroplane. Guys, with circular motion, the direction of the centripetal force is always towards the center, or always towards the middle, or always at right angles to the direction of motion. Question number 6. An athlete of mass 64 kilograms is bouncing up and down on a trampoline. At one moment, the athlete is stationary on the stretched surface of the trampoline. Figure 3.1 shows the athlete at this moment. State the form of energy stored due to the stretching of the surface of the trampoline. Elastic or strain would be perfectly acceptable at this point. Part B, the stretched surface of the trampoline begins to contract. The athlete is pushed vertically upwards and she accelerates. At time t equals 0, when her upwards velocity is 6 meters per second, she loses contact with the surface. Calculate her kinetic energy at time t. In other words, here all they're looking for is kinetic energy is a half mv squared, or mv squared divided by 2. We know her mass already. They've told us the velocity of 6 meters per second, so it's a half times 64 times 6 squared, which gives you 1200 joules. Calculate the maximum possible distance she can travel upwards after time t. Now this is a reversal of a question that's been asked many times, where you would have been given the GP at the top and you're being asked to realise that the GP at the top is the same as the kinetic energy at the bottom if no energy has been lost or transferred into other forms. Here they're doing the complete opposite. What they're saying is, look, if our energy at the bottom is 1200, and if you were to ignore air resistance, what's our gravitational potential energy at the top? Well, if no energy has been lost or transferred into anything else, kinetic energy at the bottom is going to equal gravitational potential energy at the top. So what you're supposed to do is GPE equals mgh. But this time you know the GP at the top because you know the kinetic energy at the bottom. So height would have been GPE over mg. In other words, 1200 divided by 64 times 10. In other words, 1200 divided by 640. And that would have given you 1.8 meters. If you made a mistake in the first part, error should have been carried forward in the second part. Part 3, in practice, she travelled upwards through a slightly smaller distance than the distance calculated. Suggest why this is so. Well, I've already hinted towards it. She's going to be doing work against air resistance, or, she's going to lose energy in the form of air resistance, which is regarded as heat or thermal. Part C, the trampoline springs are tested. An extension load graph is plotted for one spring. Now we're mixing energy again with forces. This is Hooke's law, but fortunately it's a much easier version, or a much easier part of Hooke's law. State the name of the point x. Well, x is the limit of proportionality. State the name of the law. Well, I've already suggested it. It's called Hooke's law. So notice again an energy and force question being mixed together, just like it was in the previous question. Question number 7. Complete the following statement. An object in equilibrium when both the forces up and down the way and the clockwise and anti-clockwise moment on an object are 0. This question was fairly badly done. People did not get full marks. And it is in the book. And it is quite a popular question, so please understand this. Basically, the resultant force has to be 0. In other words, the upward force and the downward force overall has to be 0. Also, the clockwise moment has to equal the anti-clockwise moment. In other words, the moment, the net moment, has to be 0. A lot of people picked up 1 mark here, but they didn't get both. So really what they're looking for is resultant force has to be 0 and resultant moment has to be 0. In part B, figure 3.1 shows a ladder AB. End A of the ladder rests against a vertical wall. End B rests against the rough ground. Figure 3.1 shows 2 of the forces acting on the ladder. The only force on the ladder at A is F, which acts at right angles to the wall. The weight of the ladder is 240 newtons, acting at the center of mass of the ladder. Calculate the moment of the weight of the ladder about the point B. Now guys, remember the definition. Moment is force times perpendicular distance from the pivot. So quite clearly here, what we've got is you've got the weight of the ladder, and what's being regarded as a pivot here is the point B. So the weight of the ladder at its center of mass is 240. The distance from the pivot is 1.2. So the moment itself is 290 Newton meters. Then it says write an expression in terms of F for the moment of F about the point B. Well, they've showed you F. There it's there. And they've showed you the perpendicular distance from the wall is 3.2. So remember, it's always force times perpendicular distance. In other words, the force and the distance must be at right angles. Now I know it looks more complicated because it's not like a simple seesaw, but if you remember the definition that the force and the distance must always be at right angles, then you won't go wrong. Look here for the first part, 240 newtons, right angles to 1.2. We've got some force we don't know, and it's at right angles to 3.2. So all you had to do here was write 3.2 F. Use your answer from part 1 to calculate F. Well, they've actually guided you through this. Remember, clockwise moment equals sum of anti-clockwise moment for a system to be in equilibrium. So in other words, your 290, here the actual answer was 288, equals F times 3.2. And if you rearrange, we get 90 newtons. Part 3 was very well done. Explain why there must be an upward force acting on the ladder at point B. Well, a lot of people got a right answer here. There was many answers. To make the resultant force 0, to make the resultant moment 0, to keep the ladder in equilibrium, because there must be a downward force, because the ladder is pressing on the ground, to stop the ladder sinking into the ground. I mean, this part was actually very well done by the vast majority of students. Question number 8. Figure 2.1 shows a hammer being used to drive a nail into a piece of wood. The mass of the hammerhead is 0.15 kilograms. The speed of the hammerhead when it hits the nail is 8 meters per second, and the time for which the hammerhead is in contact with the nail is 0.0015 seconds. This was actually fairly poorly done. Calculate the change in momentum of the hammerhead. Remember, change in momentum is final momentum minus initial momentum. Well, initially it wasn't moving. So you've got mv minus mu. So the mass of the hammerhead is 0.15 and the speed with which it hits is 8. So the change in momentum is 1.2 Newton seconds or 1.2 kilogram meter per second. Even if you get minus 1.2, the mark scheme doesn't seem to be concerned by the negative. So whether you left it as negative or positive, they don't seem to be too bothered. State the impulse given to the nail. Well, impulse is equal to the change in momentum, so the answer is exactly the same, 1.2 Newton seconds. Now, when I taught you guys, I suggested when you're talking about change in momentum, leave it as kilogram meter per second, and when you're talking about impulse, which is equal to change in momentum, leave it as Newton seconds. Whilst they're both correct, I just think it makes it easier in your mind with regards to which formula you're being asked to use. Last but not least, calculate the average force between the hammer and the nail. Well, this is reorganizing the impulse formula. So instead of Ft equals mv minus mu, we have F equals mv minus mu divided by t, which is 1.2 divided by 0.0015, and you would have got 800 newtons. Question number 9. An electric train is initially at rest at a railway station. The motor causes a constant force of 360,000 newtons to act on the train and the train engine begins to move. State the form of energy gained by the train as it begins to move. Well, quite clearly that will be kinetic energy. The train travels a distance of 4 kilometers along a straight track. Horizontal track. Calculate the work done on the train during this part of the journey. Here's where mistakes started to be made. Work done equals force times distance in the plane of the force. A lot of you did not change the 4 kilometers into meters. So it should have been 360,000 times 4,000, which would have given 1.4 times 10 to the 9 joules. If you didn't leave it in standard form, it's not a big deal. The units are important, and changing the 4 kilometers into meters was important. The mass of the train is 450,000 kilograms. Calculate the maximum possible speed of the train at the end of the 4 kilometers of the journey. Again, what you're doing here is you know what the work done is. It's 1.4 times 10 to the 9. So the energy that we've figured out with the work done is equal to kinetic energy. So the work done in this case is a half mv squared. And all you're being asked to do is rearrange it to do v equals square root of 2ke over m, where ke is the 1.4 times 10 to the 9. We already know the mass of the train is 450,000. So it should have been square root of 2 times 1.4 times 10 to the 9 divided by 450,000, square root all of that, and you'll get 80 meters per second. Why do they say maximum possible speed? Because here we're assuming that no energy has been transferred to the surroundings. While students think that makes your life awkward, it's actually making your life easier because we are neglecting any energy being lost in any other form. In practice, the speed of the train is much less than the value calculated in part 2. Suggest one reason for this. Case in point, energy is being lost to the surroundings, such as air resistance, more likely friction, or you could have summed it up by drag as the train moves through the air. Because we know when an object moves faster through the air, the force of air resistance increases, but here we're not asking about the force. We're really talking about the energy that's being converted or lost. Part C. After travelling 4 kilometers, the train reaches a maximum speed. It continues at a constant speed on the next section of the track where the track follows a curved path, part of the circle. State the direction of the resultant force. Again, you're going around the circle. It's centripetal force. Which way is that force? It's always towards the centre or at right angles to the direction of motion. Again, notice how energy and forces has been mixed together in this question. The boxes on the left contain the names of some energy sources. The boxes on the right contain the properties of some sources of energy. Draw two straight lines from each box on the left to the two boxes on the right. Now, when I saw this, many students only did one, and they've put the two and from each box in bold. They've made it very clear. So solar energy is not polluting, and natural gas is not renewable. Natural gas is also polluting, and solar energy, missed an arrow there, solar energy is also renewable. Coal-fired power stations are polluting. State an advantage of using coal energy as a source of energy. Well, basically, they're much more efficient. It's easily available. It gives out lots of energy. You could have said many, many things. A coal-fired power station generates electricity at night when it's not needed. Some of the energy is stored by pumping water up to a mountain lake. When there is high demand for electricity, the water is allowed to flow back through the turbines to generate electricity. On one occasion, 2.05 times 10 to the 8 kilograms of water is pumped up through a vertical height of 500 meters. Calculate the weight of the water. Well, that's quite simple. You just do 2.05 times 10 to the 8 times 10, because weight equals mass times gravity, and that will give you 2.05 times 10 to the 9 newtons. So just to point out here, solar energy, there should have also been an arrow pointing to renewable. Calculate the gravitational potential energy gained by the water. Well, Gp equals mgh. All we need to do is take the previous answer and multiply it by 10. And you will get 1.03 times 10 to the power 12 joules. In this question, many people missed out the unit, surprisingly. Next part. The electrical energy used to pump the water to the mountain lake is 1.2 times 10 to the 12 joules. Only 6.2 times 10 to the 11 joules of electrical energy is generated when the water is released. Calculate the efficiency. Remember, efficiency is useful energy out. That's a 6.2 times 10 to the 11 divided by the total energy in, 1.2 times 10 to the 12 times 100, and you'll get 52%. Again, units are really important.